So thanks a lot, Pablo. Hi, everybody. So you see my name, but you can call me simply Carlos. It's much shorter. And basically, the idea is to tell you basically about the oldest topic in photonics for obvious reasons. So I'm going to discuss essentially the new physics that we and many other people, of course, are discovering in recent years about thermal radiation. So I would argue essentially that we're dealing here with one of the most universal phenomena in physics, and after all, essentially everybody here in this room, including myself, we are emitting thermal radiation all the time, and we do it because of the essentially random thermally activated motion of charged particles. Okay, they give rise to random currents, and these random currents are the sources essentially of these electromagnetic waves. Okay, what you learned in textbooks is that this phenomenon is basically understood in terms of the concept of a black body. Okay, this perfect absorber. And of course, the Planck's law that plays such a major role essentially in modern physics. So this is basically Planck's law in a nutshell. So what Planck essentially predicted is that the black body essentially emits falling universal radiation, okay, that we all know, that only depends on the temperature. And you see this essentially distribution for temperatures going essentially from ambient temperatures all the way up to essentially the temperature of the surface of the sun. The importance of Planck's law is that it describes in a unified manner essentially all the basic laws of thermal radiation. For instance, it tells us that the maximum of this distribution appears at a temperature was inversely proportional to the temperature, and in particular at ambient temperatures. Essentially this thermal wavelength, which is going to be really important for the rest of the talk, is basically these 10 microns. So keep in mind this scale. But it also tells us essentially what is the maximum essentially thermal power that can be emitted essentially by a body, by a black body. Okay, this is nothing else than the famous Stefan Boltzmann. And it also gives us essentially what is somehow, or at least it was believed to be, the maximum essentially radiative heat transfer exchange between actually two infinite bodies. Okay, so the rest of the talk is about showing you that there are basically ways to beat essentially these Planckian limits. Okay. And the reason is that actually this law has limitations, and this is nothing really new. I like to show this. This is the famous book published basically by Planck himself back in 1906, a book that was extremely influential back then. And if you go to page number 2, you don't have to read too much. Okay, Planck explains essentially that the assumption behind essentially this law is that all physical dimensions are much larger than the characteristic wavelengths. Okay. So then it's easy that we can beat or expect at least violations of Planck's law into different regimes, okay? And this is related to the outline of this talk. So we can bring, for instance, bodies sufficiently close. Sufficiently close means below this 10 microns at room temperature, and in principle we should expect essentially deviations from Planck's law coming from the near field, something that should be easy to understand essentially in this community. But also if you go even to the far field, but if you deal essentially with bodies that are smaller than this characteristic wavelength, they are basically, you know, in principle, you should expect deviations from Planck's law, and we have understood actually that you can overcome all these Planckian limits, okay? So that's basically the goal for today, to tell you a couple of stories related to these two different regimes, and essentially with the skew, since this is a school, to give you the basics, okay, of the, you know, the new point of view on thermal radiation, okay? Of course, I have to start with the most important slide, okay? So basically everything I'm going to say was part of the thesis of Victor Fernandez, a very talented PhD student that just graduated 3 months ago, and unfortunately for us, left for consulting, okay? But I learned this morning that probably that's the way that in a few years he will be funding essentially our research, so maybe we shouldn't be so pessimistic, okay? And these 3 persons play a major role, and hey, they look familiar to you, right? Okay, so Francisco was also the co-advisor of Victor. Johannes has been involved essentially in all the stories that I told you, and Antonio gave us a crucial input essentially in the far field stories. So again, also we have to acknowledge collaboration with Homer Wright from the MIT. Okay, this is going to be a theory talk. I'll keep it easy, okay, in particular because still my cochinillo is moving around, okay. But I'll be showing a lot of experimental results that are coming basically from the group of Preimod already, and Edgar Mayhofer, basically in the Department of Mechanical Engineering in the University of Michigan, with whom basically we have been very fortunate to collaborate over the last 5 years or so, okay. let's get started. Let's go to the near field, which is very much related to the main topic of this school. And for you, it's easy to understand what makes this near field so special when it comes to thermal radiation. So imagine that I take two infinite parallel plates, okay? One hot, one cold. So typically, essentially, I can exchange heat via basically propagating waves. And this is in particular true if I have this gap being much larger than this characteristic wavelength, okay, that I told you that room temperature is 10 microns, okay? You know very well, probably better than I do, okay, that that's not the whole story. In principle, you have these evanescent waves coming from total internal reflection, but if the gap is large enough, they don't make it to the other side, and therefore they do not contribute to the heat transfer. But of course, if I go to sufficiently, small distances, or if I bring close together essentially these two parallel plates, these guys start to give me a crucial contribution, and actually they may entirely dominate the physics, okay, behind this phenomena. Actually, not really new. This was actually put in firm terms in 1971 by these two gentlemen, actually two Dutch guys working at Philips back then, okay? And they were using essentially what is called fluctuation electrodynamics, that is something that I'll try to explain essentially in a few minutes. The basic result of these gentlemen here were, okay, they look at the simplest system you can imagine, two infinite parallel plates at different temperatures separated by a certain gap size. If you look at the heat conductance due to radiation, so power divided by the temperature difference as a function of the gap or the separation between these two guys, you get the following results. Just pay attention to these solid lines. These are for different materials. This is silica. This is silicon carbide, two polar dielectrics. But you also see metals like gold and platinum. Important thing is, if I put the black body limit, you see that there are large separations, okay? In the far field regime, essentially we're not able to overcome this Planckian limit, as expected. But if you look basically at this range here, actually, in principle, you can overcome essentially the Planckian limit actually by many orders of magnitude. Just to give you a flavor, I mean, if you actually want to, overcome this limit by sizable amount, you have to go really to gaps relatively small on the order of basically 100 nanometers. And that was the challenge for many, many years. Okay, 71, we jumped to 2009. I don't know what's wrong, the quality is not very good. I'm in the projector, but hope you can see it. So we jumped almost 40 years, just to give you a flavor, essentially, of the difficulty of doing these experiments, because you have to actually take typically microscopic objects and make sure that they are actually parallelized, okay, correctly. And on top of that, you have to measure these signals. So without going into the details, basically, like 10 years ago, several experiments convincingly prove the idea that you have an enhancement due actually to these near field contributions, okay? And the community is really excited because this may be used in different applications, although this is still in some cases far-fetched. But in particular, the idea that you could use near-field radiative heat transfer to actually enhance the performance of thermophotovoltaic cells, I think at some point it will be done. Okay. So let me tell you a couple of stories briefly with excuse to actually explain the physics. Okay. So if I'm not able to do it, just stop me and pose questions. Let's start with something really simple, actually. I mean, our first project essentially in this business. We also want to control essentially light-matter interactions in the nanoscale. Okay, in our case, it's thermal radiation. So we're interested in essentially in nano devices. So if near-field thermal radiation is going to have any impact in nanotechnology, we have to show actually that you get these enhancements actually in thin films. Okay. Films with dimensions in the nanometer scale, okay? And this is what we set here to demonstrate. So now it comes our colleagues, a very ingenious essentially setup, where essentially the basic idea in this case is to look at the radiative heat transfer between the silica sphere and this multi-layer system. Important thing is we have a silica layer here. We can play around with the thickness, going all the way down to tens of nanometers. And here below we have gold, which is essentially a mirror in the infrared, okay? So these two, the receiver or the emitter and receiver, are mounted essentially in these membranes, and these membranes typically feature essentially these platinum lines. Those are resistors that you use to either determine what is the temperature of the system or to control actually the temperature, okay? And on top of that, you have to basically control what is the gap, okay? I'm not going into all the details. Let me summarize the main results. So I'm showing here the near field conductance due to radiation, and only the near field, which is subtracting actually the far field contribution as a function of the gap, the separation between the silica sphere with this diameter of 50 microns, so relatively big, okay, and this multi-layer system featuring our silica field, okay? You see, we go from 10 microns all the way down to 20 nanometers, okay? So this is actually really, really challenging. The different results correspond to different thicknesses of the silica layer, and you can see basically that there's an obvious difference when we go to large separations between the different thicknesses, but as you go to smaller and smaller and smaller gaps, these signals become comparable. So it means basically that a thin film of only 50 nanometers is able to exchange as much thermal radiation as essentially half a kilometer of your material, okay? So why is that? Obviously there must be a surface phenomenon going on here, right? I mean, so with theoreticians we have to describe this thing, so let me flash essentially what is the main framework we use, our standard model, okay? The standard model of thermal radiation. This is due to Ritov. It goes back essentially to the 50s. This Russian scientist was working essentially on microwaves, and he combined essentially Maxwell equations with the so-called fluctuation dissipation theorem. This theorem, in words, tells us that whenever you have dissipation, it's always accompanied by fluctuations, okay? And in this case, fluctuations in a material results essentially in the emission of electromagnetic waves, okay? What we have to do in practice is to look at these Maxwell equations, okay, for our combination of materials, and we have these sources. These are electrical currents that vanish on average. This is the source of the thermal radiation, but their fluctuations are given basically by this famous theorem, and tell us that these fluctuations are actually local in frequency, in a space, but they depend on the dissipation essentially in your material, which is simply the imaginary part of the dielectric function. And of course you have basically a little bit of quantum mechanics. You have this function here that is essentially the Bose function that is telling us that only the electromagnetic modes that are thermally occupied contribute to the thermal radiation, okay? So we put essentially, so this is 99% classical electromagnetism, and at the end we put H bar, okay, to gain some respectability, okay? So actually I've been doing quantum physics my entire life, so I'm hoping to go away from that, okay? But this is easier said than done. The final goal is, of course, to compute what is the Poynting vector in every point essentially of your structure. So you need the fields. So actually you need to solve these equations, and in general, depending essentially on your geometry, combination of materials, this can be basically almost impossible. And part of the community, the theory side, has been essentially trying to combine numerical methods, okay, well known in electromagnetism, actually with this framework to solve different problems. Okay, back to the problem we have in mind, this silica sphere and this multi-layer system. It still looks complicated. Okay, let me put it a surface then, okay? So to explain the physics, and I'll go back essentially to the sphere. Okay, we have to solve this geometry, Maxwell equations, we have translational invariance, okay, then it gets much easier, and it's actually basically an exercise that most students can do. And if we look at the net power as changed when they have a temperature difference, is given by this formula. It's the only one that I want to explain essentially in this talk, okay, and because I find it really illustrative and fun in some sense. So this power depends basically on two integrals, one on all the wave vectors parallel to these interfaces, and of course on all the possible frequencies, okay? The key quantity here are the transmission coefficients that give us the probability for the electromagnetic modes to go around. So this is basically the two fundamental polarizations, A and P, or if you like, TE and TM. And this is again essentially the thermal photon energy, so you see here the Bose function. So most people here are working on kind of nanophotonics, something related, but my entire life I've been working in nanoelectronics, and this is called the Landauer formula. Okay, so I was trying to move away from essentially nanoelectronics, and funny enough, we ended up with exactly the same formula, okay? It's a bit ironical, but on the other hand, we have so much experience essentially with this that, okay, we make quick progress. So we need these transmissions, and this is a simple exercise that you do in optics, okay, for the two polarizations. The only thing that I want to emphasize is that you have two contributions. One from propagating waves, the other one from evanescent waves, okay? They decay exponentially inside this gap here. Okay? So if you ignore these evanescent waves and you say, okay, the probability here is equal to 1, you go back to black body. Okay, you go back to Planck's law, to be more precise, the Stefan-Boltzmann law. Okay, but here you have to take these two contributions into account, and at short distances, actually this one is going to dominate. Okay, you use these analytical results to compute essentially the structure that I have in mind, and you see that, okay, as a function of the gap, if I go essentially to the far field, I get different contributions, okay, so it really depends on the thickness, but if I go really to small gaps, and small means smaller than the thickness of this silica film, I get a result that does not depend on the thickness, okay? So why is that? There are different ways to understand this, okay? One of the things you can do is to plot the different contributions you get from evanescent and propagating waves, and you see that for small gaps, always basically the TM modes dominate. For you means immediately surface waves, okay? You can look essentially at the spectral conductance, meaning the conductance per unit of frequency, in this case photon energy, and you see basically that for all cases it's completely dominated, this is a logarithmic scale, by two peaks, so two given energies. And this is an important message for the students here. This has nothing to do with the broadband Planck distribution. Okay, so we get thermal radiation here that is actually bichromatic. That's the other opportunity that we get essentially in this field, the opportunity to actually tune the spectral properties of thermal radiation. Okay, where are those two energies? Okay, actually these are the two energies. This is the electric function of silica, and these are the two essentially energies related to the optical phonon modes that you get in this material. So actually what is happening here is they have a strong interaction between radiation and the optical modes, and they are giving rise essentially to phonon polaritons. And they in turn give rise essentially to surface waves. So we're dealing here now with surface plasmons. They live high up for us. Okay, these are surface phonon polaritons that are thermally occupied actually at room temperature. And if you want to prove this rigorously, you can look at the dispersion relation of these modes, and you can show that actually they describe very nicely all the features you have in these transmission functions. So there is very little doubt that simply all the thermal radiation is being governed or determined or dominated by the surface modes. But something fancy is, or funny is, these are actually cavity modes, okay? They are living basically in the two systems, okay? These are hybrid modes, and when you look at the penetration of these modes, it turns out that numerically they more or less are equal to the gap. So I make the gap smaller, and they are more concentrated to the surface. Okay, and that's the reason why finally essentially all the radiation is coming from the surface, and therefore it's essentially independent on the thickness of the silica film. And actually you can visualize this. We like to visualize things. You can plot actually the field distribution related to these modes, and you see it. Okay, for small gaps, okay, you see that these modes do not depend on the presence essentially of the gold layer there. But if you go to large gaps, of course at some point when you have a thin film, these modes are going to see essentially the gold, and they are much less efficient, okay? And that's the reason why you see a difference between all these films in the far field regime, okay? Of course, I haven't forgotten that I have to compare essentially with the actual system, okay? So I use a little trick essentially for the specialists. Is well known. This is the so-called proximity effect, where I use essentially these results of this structure to actually take into account the fact that I have a curvature, okay, that I have a finite radius in my sphere, okay? So without going to the details, this is what actually explains that all these contributions for the small gaps actually are slightly different for the different films. It's simply because you still see the curvature essentially of the sphere. Okay, so a simple story, and really simple for us as well, but that was the first step actually to move to something that we consider much more fundamental, that is to push actually this physics to the limit of actually nanometer gaps, okay? You have to keep in mind that most of my career has happened essentially with very much related to single atom and single molecule. So for us the question is always go smaller, okay? So we're going smaller here. We're going essentially to gaps definitely below 10 nanometers. And the motivation was that most of these experiments that I at least mentioned essentially explore gaps up to 20 to 30 nanometers, and they are well explained by our standard model, okay, fluctuation and electrodynamics. But it turns out that there has been a group for more than 10 years looking actually at these nanoscale gaps, okay, with scanning thermal microscopes, and this is the group of Achim Kittel in Oldenburg in Germany. And making a long story short, because there are many papers, the claim is that when you go to gaps on the order of 10 nanometers and below, essentially signals, the experimental signals, are 3, 4, and even more orders of magnitude larger than what is predicted by the standard model. So Houston, we got a problem, right? So these guys have been questioning essentially the fundamental theory, at least in these small gaps. And okay, maybe there are other mechanisms that we're not taking into account. If you go to very small gaps, maybe there are something like long-range phonon tunneling, or maybe there are other carriers that we don't know that are actually contributing. Okay? How to go to the nanometer scale? In our case, it's actually straightforward because we have done it before in the context of nanoelectronics, and it's by using these scanning thermal probes. This looks pretty much like a standard AFM probe, but when you look inside, it has an anion-like structure with different layers, and the important thing is that you have chromium and gold here touching at a single point and being isolated by the silicon nitride. This is a thermocouple. This is our thermometer. This is the thermometer we use to measure what is going on essentially at the apex of this tip. And this is how we're going to measure actually the radiative heat transfer between a tip and whatever substrate you want to explore. Nice thing about this is you can coat it with whatever you want to study, silica, as in the previous example. You can put gold if you want to explore metals, and you can do all kind of combination of materials. As I said, this is nothing else than an AFM tip. So you can mount it essentially in a silicon cantilever and use it in the spirit of AFM. And this means in practice that you can go all the way down to gaps, in our case, because of the stiffness of these probes, on the order of 2 to 3 nanometers. But actually, with certain improvements, you can go essentially to picocavities, if you like. These days we're looking essentially at distances on the order of a couple of angstroms, okay? And that's the idea. Okay, so let's go for results. I don't know what is going on with this. You have one of these expensive computers, and then at the end you get this lousy. Sorry for that, okay? Two characteristic results. This is silicon silica. Silicon the tip, silicon the substrate. Just a flat surface, okay? And this is the conductance as a function of the gap separation, and the novelty is that we go from 50 nanometers all the way down essentially to 2 nanometers. And then the AFM tip typically snaps in, okay? The same thing for gold. And the difference between silica and gold is the signals here are much bigger, and you get a more rapid decay, essentially the signal as a function of distance. Probably these numbers, the scale is picowatts per Kelvin, don't tell you anything, but if I focus on this, the smallest gaps, and I compare somehow essentially with black body, this is 4 orders of magnitude larger. So we're beating essentially Planck's law by 4 orders of magnitude in this case. Okay? So how to understand these results, okay? And how to check whether this standard model is actually true. Okay, actually now we have to work a little bit harder because look at these tips. Now I cannot use my trick essentially with these surfaces or spheres. So we need more sophisticated methods, and just to give you the keywords, we use essentially this fluctuation surface current formulation of this problem. It was put forward by Alejandro Rodriguez, by Homer Wright, and Stephen Johnson in the MIT, and actually Homer Wright implemented together with the boundary element method essentially in this code that is open source. Okay, so you can go and actually use it. The advantage of this is that you can combine it with a surface method like the boundary element method, which is extremely mature. Okay, and you just need actually, when you model one of these systems, to discretize the surface. Okay, which is obviously advantageous in this case. And we went crazy, and Johannes actually said, yeah, we can model even the roughness of these tips. I said, you gotta be kidding me. I mean, no, he was not. I mean, he's Austrian. Sorry, it's an easy joke, okay? So you see the details essentially that we try to reproduce, not only the shape, so the angle of these tips, but even essentially the roughness, which we estimated that is on the order of 10 nanometers. But we don't know all the details. So we have to do some statistics, and actually the way we do it is we calculate these heat conductances by doing essentially simulating a number of tips, in this case 15, very much like in the experiment. So these are the theoretical results out of our simulations, and for the exact numbers of the experiment. And the novelty is that you see 2 results. One is with ideal tips, no roughness, and you know the result essentially of 15 different tips with this roughness on the order of 10 nanometers. Notice that it's more dramatic, the effect of the roughness in the case essentially of the silica than in the case of gold, and this hopefully will become clear in a minute. Okay, the physics, that was, I mean, still I have to tell you how well we are able to reproduce these experimental results, but let me explain the physics before. One way to do it is to look at the spectral conductance, and once more you see that in the case of silica it's completely dominated by two peaks, and you're familiar with those, right? Okay, so these are again surface photon polaritons that are dominating the entire physics in this case. The difference is in the case of gold, you can see that you get a broadband distribution, okay, and actually you can show, okay, that is actually due to the fact that in this case the radiative heat transfer is dominated by total internal reflections. These are modes essentially that are evanescent in the vacuum gap, but they are actually propagated inside gold, okay, which is slightly different. Let's see what is going on, okay? We need to see things. We need to see things. So what you see here is basically the tip, the sample, the same case, silica, gold, and the gap in this case is 1 nanometer. And we're plotting essentially, this is a map of the Poynting vector projected on the surface of these systems. And you see that all the radiation in this case, look at the scale, is coming from the very last, essentially, nanometers. Okay, although you have a microscopic tip, essentially the thermal radiation is entirely dominated by what is going on in the last, let's say, 10 nanometers. For me, it's absolutely mind-boggling, okay? So, in the case of gold, because we have these different modes that are propagated inside, actually, even if for these small gaps, they are coming basically, you know, you have a big contribution for a large, from a large portion, actually, of the gold tip, and this also explains why, in the case of gold, the results are not so sensitive actually to roughness, okay? An important thing, what about essentially the comparison with the experiment? This is the actual comparison between theory and experiment, and it's a comparison. This is as close as we get essentially to first principles, okay? So there are no adjustable parameters here. This is basically a comparison and you can decide yourself. I mean, this is an excellent demonstration essentially of the fact that the standard model actually works, at least all the way down to these gaps on the order of 2 to 3 nanometers, and by using basically even the local approximation for the dielectric constants, meaning that for us they only depend on frequency, they don't depend on the wave vector, okay? So then after the years we have been doing different things in this topic, mainly related to how we can control these things with systems where we can break, for instance, reciprocity by applying magnetic fields and doing other kind of stuff. But actually in the last years we bump into what I think is a beautiful surprise, okay, it was at least a surprise for us, which is the fact that we can actually beat the Planckian limit even in the far field, where you only have propagated modes, okay? So let me tell you a story. Okay, this is a summary of 40, 50 years of work, so I'll do my best actually to condensate this here. We have this question, can we beat the Planckian limit in the far field? Okay, so we're not the first to tackle this. What is known is if you get actually infinite system surfaces, even if they are nanostructure, no way. You can prove that you cannot beat the Planckian limit. But what if I go essentially small, okay? Remember, this was one of the limitations of Planck's law. I can go south wavelength, at least one of the features of my body, okay? Actually, there has been some work, okay, over the years showing that there's no fundamental limit actually in this case. If we go to a small objects, in principle, nothing prevents to overcome this basic law, okay? And I'll explain, and this will become clear in a second. But actually, in practice, nobody has shown this experimentally, and there is only a couple of works, theoretical works, showing that you can actually overcome this in rather academic situations. But all the experiments looking at the, the radiative heat transfer or the thermal emission, essentially of small objects, the small means short wavelength in this case, have failed to show actually super Planckian radiation. Okay, so is it actually possible? Well, the answer is yes. This is what we show essentially in this paper that was published essentially in January this year, and that took us essentially quite some time, okay, to actually complete the story. But now we have a full picture of the super Planckian far field radiative heat transfer. The idea goes as follows. Maybe you're wondering now, but you have a standard model, you have an exact theory, so then it's not a big deal. If there is super Planckian radiation, you should be able to find it, right? Well, there's a problem that we have to emphasize here. So until very recently, all these numerical methods were not available. It's only now that we're able actually to look at the radiative heat transfer between objects with arbitrary size and shape. And still these systems or these models and these techniques, okay, are not perfect. There are many systems, basic systems, that we're not able to handle, okay? Then also you have to keep in mind that there are simply many possibilities in terms of combination of materials, shapes, sizes, etc. So we need a guiding principle, a recipe if you like, okay? In our case, this came basically with this following analytical results that I'm going to illustrate in the simple case of two spheres. So the power exchanged by these two guys in the far field, actually really in the stream far field, can be written in this way. You have the area of the spheres, you have a view factor, okay, which is a geometrical factor that includes the information of the separation and the solid angle that they see each other. You have essentially the Planck's distribution that you know by now, okay, it's plotted here at room temperature, and you have this guy here, which plays the role of an effective emissivity. And this guy is the absorption efficiency, meaning is the ratio between the absorption cross-section and the geometrical one. You say, okay, so what about the black body limit? Black body limit actually means that Q, capital Q, is equal to 1 for all frequencies. So then the recipe is simple, right? I just need this guy being larger than 1 over a broad band, okay? And from the scattering theory of small particles, you know that in that case, essentially Q can be larger than 1. This is really well known, in particular here in this community, right? But you'll see that it's not that easy, okay? And this is what I try to illustrate in this crowded slide, okay? That you take the spheres, you can compute essentially these efficiencies, okay, for metals or polar dielectrics, and look at here, okay, silica. Sometimes you see values larger than 1. These are mean resonances well known essentially in your community, okay? So then what's the point? Well, if you look actually to the thermal conductance and we normalize things with a black body result, you see that all the values, no matter essentially what is the distance between the spheres, no matter what is the radius, is basically always below 1, apart from basically very peculiar cases. So in spite of the fact that sometimes we get this resonant absorption, actually we don't see the super Planckian essentially radiation, okay? And you now understand why. It's not so easy. I need to get a broadband actually absorption, okay, to actually beat the Planckian limit. You go to other simple systems and no way, you fail again. These are cubes and same conclusion. But remember, I mean, if we go back to this formula, this is telling us, okay, what matters is this ratio. Let's play in a funny game. Let's keep constant essentially the geometrical cross-section and let's try to increase the absorption. How to do that? Well, I can do the following, for instance. I can start, no spoilers. I can start with a cube, okay, where I don't get this super Planckian. But now I can elongate this, right? I'm going to give more space to the absorption, to the radiation, sorry, to get absorbed, okay? Simple game, okay, very simple idea. Okay, so I go from these cubes essentially to these nanowires or parallelepipeds, whatever you like, okay? So you see what I'm doing. I keep fixed these lateral dimensions and I'm going to elongate this. I'm going to change this length here. And all of a sudden I go from values of the efficiency way below 1 to values really huge ones and over a broad band, okay? If I translate this into essentially the thermal conductance, all of a sudden when I start elongating this, when I get to systems on the order of few microns, I can overcome the Planckian limit and look at this, okay? So if I put here 50 nanometers of this silica or silicon nitride, I can get 3 orders of magnitude over Planck's law, okay? Here there are several things to say. We have lines essentially for different gaps. Those lines were computed in general essentially with this numerically exact method, okay, the SCAF EM that I mentioned before. But the final result in the stream far field case for very large gaps is actually the analytical result, okay, where the only input that you need is the cross sections, essentially the absorption cross section of these systems. Okay, so it shows that the formula actually works, and it shows that you can beat the Planckian limit, and it shows something that you may say, okay, so what is the point? Is this a super Planckian emitter? If I take one of these wires and I compute the total emission, and I compare this with black body, it's lousy. Actually, you get values way below 1. This is even below 0.2. So the point here is we have a very anisotropic, okay, emission or absorption. Okay, it's the anisotropy of this system that is making basically preferential the radiation to go along this direction, which is the direction that we test when we look at radiative heat transfer. Okay, so that's nice, but if you put the absolute values, there's no way to measure this. Okay, so can we predict this for a realistic system? And then our colleagues in Michigan drew our attention to these systems that I personally didn't know. Okay, these are called suspended pad micro devices. These are widely used to measure actually the thermal transport of nanowires, okay, and all kinds essentially of nanostructures. So these devices are simply formed by two adjacent silicon nitride membranes that you can see here, and they have huge dimensions. At least the lateral dimensions are on the order of 50 microns, okay, 50 by 50. But they are very, very thin, typically below 1 micron. So we have essentially two dimensions are really large, but one is definitely sub-wavelength, okay? And that's basically what we need in order to see the Planckian, the super Planckian emission, okay? I have to adapt my formula because these systems are not exactly isotropic like a sphere. Now I have to take into account essentially the two basic polarizations, essentially along this direction if I'm in the extreme far field, okay? So now comes essentially the main result. Okay, so if I take, for instance, these suspended pads made of silicon nitride, these huge dimensions, but now I play around with the, essentially the thickness, I see the following. If I look at these normalized thermal conductance, normalized with a black body result, what I see if I go to very large thicknesses is what I told you. I cannot get any super Planckian. These different lines are for different, essentially, gap sizes in the far field regime. But as soon as I, decrease essentially the thickness below the 10 micron, I start to see super Planckian. If I go to 100 nanometers, I can beat again essentially the Planckian regime, or the Planckian limit, sorry, by more than 3 orders of magnitude. Okay, and these are systems that are already available essentially in the literature. If you want to see basically what is going on, I'll skip most of these things. But what happens at the end, these systems are extremely efficient absorbing the radiation, because at the end of the day we discovered that these are dielectric waveguides. Okay, it was really funny, and you see it here actually a simulation essentially where you see the absorption of a plane wave, and you see that the field is actually distorted in a scale that is 100 times larger than the thickness of the pad. Okay, this explains these huge values of the efficiencies. And you can go on and analyze things actually in terms of the electromagnetic modes that are sustained actually in these waveguides. Okay, well, these are details. If you want to know more, you can ask me. Okay, so we were extremely happy. We thought, okay, we have bumped into something fundamental. We submitted the paper to Nature Photonics. The editor was absolutely enthusiastic. After 2 hours, was with the referees, and the referee said, "Oh, I'm not surprised. Oh, this must be known. It's true that I'm not able to give you any reference, but this must be known." And they're like, okay, so but give me a single reference. No way. So it's not surprising, but it has not been predicted essentially more than 100 years of this field. Okay, so actually Victor got really disappointed. It probably goes to one of these secret, side of science. Maybe we should read your book more in detail, and we don't understand it. We try to explain essentially, Victor, look, I mean, be patient. Essentially at some point, and the experiment is going to show that you're right, so it will be fine, okay? So this happened essentially last week, okay? It appeared online in Nature, this paper where you see what I told you, okay? So the dimensions are basically the same, gap size 20 micron, which is enough to be in the far field. And you see the lateral dimensions, 60 by 80 microns. They are huge membranes, okay? And they can vary the thickness between essentially 300 nanometers to essentially 10 microns. So actually to explore this crossover I was talking about. The bottom line, the main result is this one. When you look at the radiative conductance as a function of the thickness of these devices, you see that if you go to very large or very thick devices, basically the solid line almost coincides with the expectation from black body, okay? But if you make the devices thinner and thinner, you see essentially that you get an enhancement that in this case is of 2 orders of magnitude, confirming the idea that you can actually beat the Planckian limit in objects that are basically macroscopic, okay? But at least one of the dimensions is really small, okay? And actually this is Victor's results, okay? and basically reproducing these things. This is the same graph I showed you before, and this is where our experimental colleagues are. Essentially, we get, in this case, 200, not 100, and it's because Victor understood long ago, essentially, that the beams that you have, essentially, you know, you have to hold, essentially, this membrane somehow. Actually, they are made also out of silicon nitride, and they do play a role, okay? So these, actually, simulations are huge ones. They take us, essentially, weeks and weeks, essentially, in our best computers, okay? So maybe you're wondering now, wow, Victor is working in consulting. It takes weeks and weeks, and he was able to reproduce all the experimental results, essentially, of a paper that appeared in Nature last week. He's good, but not that good, okay? This result is actually 2 years old. It was part of our collaboration with our colleagues, but we failed, essentially, to find a way to write a common paper. This can happen. What I'm not so happy about is the fact that in the Nature paper, essentially, our work is not really properly mentioned. Okay, they don't acknowledge, essentially, that the whole theory that they provide is simply repetition of Victor's calculations. Okay, this is part of probably not the secret side of science, but the dark side of science that we hope, essentially, Nature will fix soon, essentially, to be a little bit more fair. I have a minute, okay? So let me flash something because I actually don't want to get into the details. Once you understand one of these things, immediately there are many new questions, okay? And the fancy question for us was, when you look at these results, you beat more and more the Planckian limit when you reduce, essentially, the thickness of these devices. But then we immediately ask ourselves, so what is the limit? What if I make it thinner and thinner? So remember my question. Okay, let's go to the single atom limit. We're theoreticians. We can play this game, and we can explore what happens if I replace these membranes by 2D materials, right? So what we did here is to look at graphene and also black phosphorus to show that these systems, they have a geometrical cross-section of a single atom, right? And still you can play this game. When you look at the basically how they absorb the incoming radiation, if you take a flake with these dimensions, you can see that actually in a certain frequency range, you can actually get this efficiency way larger than actually 1, simply by making longer and longer these flakes, okay? Giving a space to the radiation to be absorbed. It's just that simple, okay? So you play this game, okay, and you can go even to dirty graphene, okay? And just to point out one thing, now we beat the Planck's law by 7 orders of magnitude, okay? That's our record so far, okay? And as I said, you can do something similar actually using black phosphorus depending on the doping and the size, essentially, of these flakes. So with this, essentially, I conclude. I hope I have shown you, essentially, the thermal radiation is by no means textbook physics. There are many surprises. Actually, it's been used in not only to discover new phenomena like the one I predicted here, but for instance, Professor Fan is using now far-field radiation to do amazing stuff. Fortunately, you're not talking about this, right? Yeah, oh, sure, cool. Then this has been an introduction, actually, to his talk, okay? So with this, basically, I conclude. I think I don't need to repeat the main idea. So thank you very much for your attention.